The next section is EMF values. Now, EMF stands for electromotive force. The electro part is the electron push, the motive is the push of the electrons, and the force is measured in volts. Now, the electromotive force in volts is defined as 1 joule per coulomb. Now, what that means is a joule is a measurement of energy. So 1 joule has a particular amount of energy or work or heat, however you want to look at it, for every coulomb. Now, a coulomb is a quantity of electrons. Now, if we try to use moles for a quantity of electrons, it is so humongously large that it's impractical to use. So a French scientist by the name of Charles Augustin Coulomb decided to quantify that as a lower value. And that turned out to be 6.24 times 10 to the 18th electrons instead of 6.02 times 10 to the 23. It's a difference of about 100,000. So, there is a chart of these electromotive forces as figured out for reduction reactions in the appendix 820 through 821. It's also in the chapter, I want to say it's 836 or 856. But, I mean, you can use either one, it doesn't make a difference. I like the appendix one, it's a little bigger. But what we're going to measure is the electromotive force for each half reaction in a redox reaction. A battery is the result of 2 half reactions transferring electrons from one end to another, rerouting it through a resistor, and then coming back to the other side of the battery, which we call the ground. And we're going to then calculate based upon that in terms of volts. Okay? So, let's take a look at an example here of what I mean by reduction force now, or reduction values. The chart on pages 820 and 821 is what we call reduction potentials. Now, potential is what the amount of energy that could be created between the 2 ends of the battery. And it looks only at the reduction half reaction. So if I take a look at this half reaction, where chromium-3 is being reduced to chromium, the reduction value for that is measured as a negative 0.74 volts, or negative 0.74 joules per coulomb of electrons. If I want to find the value for the oxidation version, in other words, if I take that reaction and flip it, the reduction value is going to be the opposite of the oxidation value, or the oxidation value is the opposite of the reduction value, depending on how you want to look at it. In this particular case, this is the exact opposite of this right here. So the value of the EMF is going to change from a negative to a positive, 0.74. We write here E sub red is negative 0.74, and E sub ox is positive 0.74. And again, the little zeros there just designate a standard condition, like 25 degrees Celsius, 1 atmosphere, and if it's a concentration, 1 mole per liter. Not important. It's just a good idea to keep putting little dots up there. Now, we can use that in determining the half reactions for an E cell is going to be the sum of the two. So that's going to be E red plus E ox. And remember, when you get the oxidation values, you have to change the sign on this chart in order to use it. But what you do is you take a look at you have to take each reaction, break it down into its half reactions, find the values on here, remembering that the oxidation reactions are going to be the exact opposite of how they're written in this chart, and then add those values together, and you have it. And this is an example. One of the first batteries ever made was a copper zinc battery. And so the 2 half reactions were involved. Zinc here going to zinc 2 positive. The oxidation number is increasing from 0 to +2, so that's your oxidation value, zinc to zinc, 2 positive plus 2 electrons. If you look for that reaction in here, it's not there because it's an oxidation. So the reduction, however, you flip that you can find on here, and it's a negative 0.76 volts. But we want the oxidation. This is the reduction, so we change the sign from negative to positive. The positive 2 copper gets reduced to copper 0, and so that is found in here, copper 2 positive, copper 0. You gotta be careful, this is copper 2 positive, copper 1. You don't want that one. And this is 0.34. So the E cell, the EMF, the force of the cell is going to be 1.10 volts. And that's going to be a spontaneous reaction because anytime E cell is greater than 0, it's going to be considered spontaneous. And the bigger the value, the more spontaneous it's going to be. Sometimes you need a little extra something to add to it, but then it'll get going. But if it gets really big, it goes like gangbusters. So that's an easy version of what you're going to be doing. On the other side of the spectrum of easy and toughness, we have this reaction right here. The first thing you need to do is to go through and find your oxidation reactions and reduction reactions by finding the oxidation numbers. So I've got 0 for this because it's by itself, 0 for this because it's by itself, no charge in either one. This is by itself, it has a charge of positive 1, plus 1, we ignore the 12, 3, and 4. That's got nothing to do with what we're trying to do, that's just a balanced equation. But we don't need that, we just need to find the half reactions in whatever form it's given in the chart, okay? Positive 3 for this, so that means the aluminum's being oxidized, and when that goes from Al to Al3 positive plus 3, that sure enough is found in the chart. Only its value is a negative 1.66 volts, so we had to change it to positive 1.66 volts. This one's a little trickier, going from oxygen 0 to oxygen negative 2. Okay? Now, so you're going from oxygen to water, and then you find the half reaction that's in there. As it's written right here, it looks like this. This is the reduction reaction for it. And you get, according to this, 1.23 volts. So your E cell for the whole thing, 1.66 plus 1.23 is 2.89 volts. Again, it's positive, therefore it's spontaneous. There you have it. We have 5 practice problems that will be just like that. And have fun.